Hello, let's start off our first video about computer arithmetic for complex networks, chapter 4. In this chapter, we are going to look on standard for floating point arithmetic, right? In this topic, first of all, I'd like to give some background. As you know, numeric computing is a vital part of technological infrastructure and scientific knowledge. Virtually all numeric computation uses floating-point arithmetic. Almost all computers, and that's true, almost at least 90% use the IEEE standard for arithmetical floating point. However, it's clear that important aspects of IEEE standard are still not understood by many students and even for professionals. Numeric computation means computation with numbers. It's an area as old as human civilization itself. Around 1650, the Egyptians already employed computing techniques. Counting stones and sticks has been used for years to count and store numbers. Abacus was used in Europe until the introduction of decimal position notation. So this is a very basic, but just to see that that's importance to store numbers. So numbering on abacus. So here you can see the 0 to 9, and this in this here it's what number presented. So there is no movement of this. So in this case you have 0 because there is no movement, 1 because you get the one of the stones here, one of the cells to go up, 2 and so on and so forth. When you got 5, instead of moving here, you are going down, then up, and you are going all the stuff have 5 up and 4 down, so you have 9, right? From the 16th century, the decimal system became the base throughout Europe. The next major advance was the tabulation of logarithm by John Napier at the beginning of the 17th century. With logarithms, it's possible to replace divisions and multiplications with subtractions and additions. Isaac Newton and Lens developed calculus in the 19th century and numerical solutions for solve various problems. Other great mathematicians such as Euler, Lagrange, Gauss are responsible for major developments in numeric computing. Another device used was the slide rule until the 70s, in the last century, right? Mechanical devices for calculation were invented by Schickard, Pascal, and Lens. Charles Babbage started to develop equipment without human intervention. It was perhaps one of the first mechanical calculations that you can see in the modern era. During World War II, there was a great development of devices for calculation, and it can be said that around this time, the computing age has begun. One of the first machines considered as a computer was the Z3, built by engineer Konrad Zuse in Germany between the years 1939 and 1941. The Z3 used electromechanical device and already used numbers floating-point binaries. The British government developed at the same time a device, Colossus, used to decode secret messages. So this is a photo. You see that the size of the computer is almost a human size. It's quite big and demands a lot of energy. Energy, by the way, it's not so important nowadays. But after started using some device embedded in small device, and you cannot see a huge development in batteries, the use of energy start again to be important in many applications. ENIAC, Electronic Numerical Integrated Computer, it's a device of about 18,000 volts and was built at the University of Pennsylvania between the years 1943 and 1945 by Eckert and Macaulay. So this is another device. It's quite famous, at least in West. So please, guys, if you have some new developments from the Russia, I'll be very glad to hear from you, right? Because sometimes from here, from Brazil, we can most have access from the West book, so probably we are losing some important developments from Asia and Russia as well. Two main scientists who influenced the patterns of the development of computation device were Alan Turing and John von Neumann. So the figure 4, Alan Turing, and figure 5, John von Neumann, these two guys, they started to work together in Princeton a long time ago. During the 1950s, the main use of computers was for numerical computation. Since 1960, computers have been used in companies to process information such as text and image. Users often are unaware that manipulation of text, sound, or image involves numeric computation. Computers are used to solve equations that model the most different systems. So this is why it's really, really important, because in this sort of modeling, you have modeling for many areas. You can model the expansion of the universe. You can model the atom. You can model some process of statistical analysis for medical data, prediction of climate, it's really important nowadays, and from electrical engineering, circuit simulations, aircraft modeling. So before you start to fly an aircraft, you usually use some models to see some training and testing and the reliability of electrical systems. The numerical results are compared with experimental results. Usually this is a very important mechanism, you know. In summary, all areas of science and engineering have use of numeric computation. So if you are a master of this technique, you can be a professional useful in many areas. The real number. The actual numbers are represented by a line. So in your first chapter, you could see that the actual numbers are represented by a line. So the line extends infinitely towards minus infinity and plus infinity. The minus infinity symbols and plus infinity are not considered numbers. The extended real number system consists of real field R and two symbols, plus infinity and minus infinity. It preserves itself original order in R, and you can write minus infinity is lower than any real number, and any real number is lower than plus infinity. Is defined for nx belongs to R. The symbol R here, so this symbol here, right, is extended number. What's the difference? In this case, you can use minus infinity and plus infinity, right? All right, so let's move on here. The real number. There's infinity but countable integers. The rational numbers, Q, are those that consist of a ratio of two integers, such as 1 divided by 2, 2/3, 6/3, and so on. Rational numbers are infinity but countable. Irrational numbers and are real numbers that are not rational. Examples: square root of 2, pi, and other numbers as well here. The number e is the limit of what? 1 plus 1 divided by n, 2n, as n approaches infinity. So if you use this calculation here, you see that as n becomes bigger and bigger, this is going to approach 2, 7, so on, right? Investigations in definition of E began in 19th century and 70, right? So every rational number can be defined as the limit of n sequence of rational numbers. The set of irrational numbers is said to be uncountable. Roman number is another way to write numbers. you can see his letters here, M, D, C, C, and so on, is equals to 1985. The positional system makes use of an essential aspect. 0 is represented by a symbol. The Babylonians in 300 BC used the symbol to represent 0. The Arabic system was developed in India around 600 AD. After the year 2 and 1200, the use of Arabic numbers began, notably due to the work of Liber Abaci, or calculation book, written by an Italian mathematician, Leonardo Pisano Bigolo, better known as Fibonacci. The decimal system requires 10 symbols. The choice is based on function of the numbers of fingers. The Babylonians had another system based in 60. 0 is required to distinguish 601 from 61. Decimal systems was initially used only for numbers whole, for integers. Although the decimal system is convenient for people, it's not happens to computers. The binary system is most useful, in which each number is represented by a word of bits. Each bit corresponds to a power of 2. A bit can be seen as a physical entity that's linked or off. In electronics, you know that the bit is represented by a level of low and high voltage. Bits are organized in groups of 8 called byte. Each byte can represent 2 to 8 equals 256 different numbers. The real number continues here some basic representation. So in the base 10, 7 to 1, you can see what does it mean, as you can represent 7 to 1 as 7 times 10 plus 1. Has its binary representation like. So if you write 7 to 1 here, you are going to, so the real number here, you are going to represent in decimal number like that, because you can make 1 times 64 plus 0 times 32 plus 0 times 16 plus 0 times 8 plus 1 times 4 plus 1 times 2 plus 1 times 1. And of course the result of that is 7 to 1. You can also make the representation of fraction number. So in 11 divided by 2 is 5.5. So in this is represented like that in base 10. And here in binary you can represent like that, right? So 1 times 4 plus 0 times 2 plus 1 times 1 and so on and so forth. Irrational numbers have infinity decimal and binary expansion without repetition. Computational representation numbers. What's the best way to represent numbers on computers? So probably nowadays the most useful is binary, but there are other challenging representation like computing the numbers. Let's see what's going on in this technical issue. Integers are represented by 32 bits. The integer 71 would be stored such as, like that. So in this way you can represent numbers from 0 to 2 to 32. So it's a number 1 or 0 to this big number here, right? The number 232 cannot be represented but because you have to use 0. So here just a small exercise, so very quick. I hope that you can use in very easy way. So just make the transformation from 1 divided by 10 to binary systems. Do the decimal and binary expansion from the following numbers. So pay attention here because you have to truncate even in the decimal part. And here it's a very important issue because what's the number of bits need to represent the number 50,000? So please, in teams, develop these questions and make this in appropriate a small report to keep in mind the proper deadline for this exercise 3, right? So here, this is the first video of this chapter. I'm going to finish now, and I hope that you have enjoyed, and I hope that you can see the next video as well, right?